Hello everyone, welcome to another episode of Discovering Chemistry with Yongbun. Today I'll be covering some chemical kinetics, which is the study of the rates of chemical reactions. Many of the concepts I will cover here are not in the H2 syllabus, but rest assured they are not very difficult, and so I'm sure that you would be able to easily understand them. There are two parts to my kinetics presentation. Today, I will be presenting only the first part, as I don't want my video to be too lengthy, right? Otherwise, I would lose you already, right? Halfway in the presentation. I'll be going through some of the fundamentals of this theory of reaction rates called collision theory. I want to bring you to understand how the Arrhenius equation, which gives the relationship between the activation energy, right, of the reaction, right, EA, the rate constant K, and the temperature at which the reaction is conducted, T, comes about. I will also be discussing some lesser known concepts, such as that of the steric factor and the harpoon mechanism. Kinetics is essentially a topic in physical chemistry that can be at times very math heavy, especially right when we talk about more advanced kinetics. In this presentation, I hope to raise your level of conceptual understanding in kinetics, which I feel is more important than learning mathematical treatments and techniques. To prepare for this presentation, I used some content from this book on physical chemistry titled Elements of Physical Chemistry by Peter Atkins and Giulio Di Paola. I find that it is a rather reader-friendly book that wouldn't bog the reader down with too much mathematical detail, unlike some other textbooks on physical chemistry. As I go along, you may see some images taken from this book, so I need to give the appropriate credits, right, for this book. So let's begin with the collision theory of reaction rates. Collision theory essentially models reactions as effective collisions between hard spheres. These hard spheres represent the reactant particles that undergo the reaction. Not all collisions are effective, only those where the reactant particles possess the minimum required kinetic energy, right, to overcome the activation energy barrier, and also where those with the reactant particles colliding in the required orientation. So as you can see here, there's red and violet spheres colliding with each other. So perhaps for this part of the image, A, the two spheres perhaps do not possess, right, the sufficient kinetic energies, so they just bump into each other and then they bounce off each other, right, remaining chemically unchanged. For the second part, you see that the two hit each other with the correct energies, and hence they come off from the collision chemically changed. So what is the fraction? What is the fraction of reactant particles that have an energy that is at least equals to this activation energy, which is this minimum required kinetic energy, right, in order for the collision to be an effective collision, right? So what is this fraction of molecules? In other words, what is the proportion of the molecules that have satisfied the energetic requirement for effective collision? To answer this question, we have to turn to statistical thermodynamics, which tells us that for a given sample of molecules, at a certain temperature, their molecular speeds follow such a distribution. So right, this is the distribution, like this curve shown here, right? At two different temperatures, two different distributions at two different temperatures. It indicates to us how many molecules, right? So the y-axis is the number of molecules. How many molecules have a particular speed at a particular temperature. So let's say I want to know how many molecules have this particular speed here, right? So at this mark where my cursor is at. So I just trace up, right? This is the number of molecules with this speed at this high temperature, right? Arbitrarily high temperature. Then if I want to know what is it at the low temperature, this speed at the low temperature, I just trace up to the low temperature, and then yeah, this is how you read off the graph lah, huh? So however, we are only interested in the fraction of molecules that have the minimum required speed that corresponds to the activation energy, and it turns out that this fraction is indicated in this shaded region. And from statistical thermodynamics, it is given that the fraction, right, of molecules in this shaded region can be given by the expression e to the power of negative EA over RT. Again, EA is activation energy, R is the gas constant, ideal gas constant, and T is the temperature, and F is just a fraction, right? So in this case, you may be wondering why we're not using kinetic energy, but instead using speed. So it's just that kinetic energy is proportional, right, to the square of speed, right? Ke equals to half mv squared. So hence it is appropriate for us to use speed on the x-axis. So the rate constant k, okay, is supposed to represent, so if you want to go back to the previous slide here, the rate constant k is supposed to represent the frequency of effective collisions. So now we know one part, this part of the expression. That is the part that indicates the fraction of collisions that meet the energetic requirement. So I wanted to reiterate this in this slide. I'll reiterate this in the next slide. So let's go to the next slide first. Sorry about this jumping around. There is also this pre-exponential factor in the Arrhenius equation, which is denoted as A, the pre-exponential, because it is before the exponential factor, right? This A is just a measure of collision frequency. It is not the effective collision frequency. It measures frequency of all types of collisions, regardless of whether they result in a productive reaction. It is derived from the kinetic theory of gases, and I shall not go through this expression in detail. However, it may be worth noting that A has a temperature dependence, which I found puzzling at first because in many of the kinetics calculations I've done before, I never took this into account. In fact, it is typically assumed, right, in my calculations that A is independent of temperature. And so I went to look this up on Wikipedia. And so if I may just direct you to this paragraph, right, this is the Wikipedia page for the Arrhenius equation. If I may just direct this paragraph starting here, given the small temperature range of kinetic studies, it is reasonable to approximate the activation energy as being independent of the temperature, right? And then note here, similarly, under a wide range of practical conditions, the weak temperature dependence of the pre-exponential factor is negligible compared to the temperature dependence of the exponential factor. Other than in the case of barrierless diffusion limited reactions, which I will discuss in the next part of the presentation, which will not be covered today. Yeah. So it turns out that, you know, my assumption in many of my calculations, which I just ignored the temperature dependence of A, was actually, it may not actually be wrong, right? So let's move on. So now we can come up with the Arrhenius equation. We have the A and the pre-exponential factor and the exponential factor. So to recap, K is the frequency of effective collisions, and A is the frequency of all intermolecular collisions. And this exponential factor is the fraction of collisions, of all collisions, that are sufficiently energetic. In other words, the collision meets the activation energy requirement. That is, the molecules contain an energy that is at least equals to the activation energy. So those who are astute among you would realize that there is something missing in this equation, and that's what we'll be getting to in the next slide. A clue I can give you is that collision theory tells us that there are two requirements for a collision to result in a reaction. But have we taken both of these requirements into account in this Arrhenius equation, or is there something missing? Often in experiments, we find that A is actually lower than the value that we get from the kinetic theory. And if we think back to the two requirements for an effective collision, the energetic and the steric requirement, right? This does make a lot of sense. So with the factor of e to the power of EA over RT, right, we have factored in the energetic requirement. But where is the steric requirement? Are we assuming that collisions are effective as long as the molecules have the required energies, but regardless of their relative orientations? Certainly we should not make such an assumption. This brings us to introduce another factor into the Arrhenius equation, that is the steric factor. This indicates the fraction of sufficiently energetic collisions that also occur in the right orientation. Right, so now with this steric factor having a value between 0 and 1, the Arrhenius equation is now complete, right? So we have the rate constant, which is the product of the, it takes into account the steric requirement, right? The molecules are the correct orientation, the pre-exponential factor, which is the basically the total number of the frequency of all collisions, and then there's an exponential factor which takes into account the energetic requirement. So with all these three in place, the equation now looks pretty complete. So more about the steric factor. So naturally, as p is a fraction, right, it ranges from 0 to 1. The smaller the value of p, the more stringent the steric requirement can be said to be for the addition of hydrogen across ethene, right? The steric factor is really small, right, indicating a very stringent steric requirement. And it has a value of 1.7 times 10 to the power of negative 6, right, an order of magnitude of negative 6. So it's really small. So maybe out of all possible orientations, really just one of the many possible orientations can result in a productive reaction. So that is why the requirement is so strict, is so stringent. So some reactions have a value of P greater than 1. Examples include reactions that proceed via the harpoon mechanism. This mechanism proceeds via two steps. Firstly, there is a transfer of a single electron, followed by then the second step, which is mutual Coulombic attraction, right, between the two ions generated. So I think this sounds a bit complicated. You may not understand it now, but let me try to bring you through this slowly, right, with some diagrams. Oops, sorry, it's not this. Yeah. So I've drawn using paint a diagram that can help to illustrate the difference between reactions that take place normally, right, with effective collisions with a value of P between 0 and 1, and reactions that take place via the harpoon mechanism, right? So typically for an effective collision, right, the two reactant particles modeled by spheres, right, must be in physical contact with each other. In other words, the centers of the two spheres, represented by my red dots here and here, must be at a distance, right, of d apart, where d is the diameter of the sphere, right? It does make sense, right? In order for the two spheres to be in contact, the centers must be a diameter apart, right? And for such normal collisions, the steric factor is between 0 and 1. But what about for reactions that take place by the harpoon mechanism? Well, for such reactions, the reaction doesn't begin, right, when the reaction isn't confirmed, right, when the reaction does not need the particles to be in physical contact to actually sort of begin, right? For the normal one here, the particles must be in physical contact, right, in order for the reaction to start. But for this one, as long as it is in some close proximity, right, of course there is still a particular distance, right, but this distance is not d, it is greater than d, it is greater than the diameter of a sphere. And so once the two particles are in close proximity, the reaction can already begin. The two particles will then be attracted to each other and the reaction will proceed. So actually it does not require, right, that much the steric requirement for the reactions that take place via the harpoon mechanism isn't that stringent and hence P can be greater than 1. So if this still sounds a bit funny, right, strange, don't worry. I will now go through another example, a concrete example using a particular reaction, right? So let's go through the reaction of potassium and bromine. I will be using this piece of lecture notes produced by the chemistry department of York University in Canada, right? York University, yorku.ca. As the author of the notes write, we can view the valence electron that potassium possesses as a harpoon. And so for those who don't know what a harpoon is, I have an image from Google Images that helps to explain what it is. So a harpoon is basically a spear that is used by fishermen to catch fish. And a harpoon can be attached to a gun to become a harpoon gun. So it's a gun that shoots out a spear, at a fish. So so right now you may be a bit puzzled why I'm mentioning this, but this does link to the example. Okay. So once a bromine molecule comes close enough to the potassium atom, the potassium atom would throw its harpoon, right? So in this case, the harpoon is the valence electron towards the bromine molecule. Once the electron or the harpoon sinks deep into the flesh of the bromine molecule, the potassium atom would pull the fish, and in this case, a fish referring to the bromine molecule, right, towards it. Potassium will pull it towards it, and physically this occurs because of Coulombic attraction, right? So in this case, why is potassium able to pull the bromine towards it, right? And it's just because now they are charged. Because once electron transfer takes place, once this electron transfer completes, the potassium now becomes a cation and the bromine becomes an anion, and hence they will mutually attract each other because they are unlike charges. So they mutually attract each other along a particular line of approach, and then once they physically contact each other, there will be some electronic reorganization, and we'll get KBr salt, and a bromine atom. Right. So I hope you understand the harpoon fisherman harpoon fish analogy, right? So some of you must be wondering, what is the maximum distance between potassium and bromine such that the electron transfer can still occur? In other words, how far can the potassium atom throw its harpoon, right? And it turns out we can approximately calculate this given data on the ionization energy and the electron affinity of bromine. So what we're doing here is basically we're considering the energy change for the electron transfer. So what are the energy changes going on? The small changes, not the overall change, the small changes. So firstly, you can of course think of the ionization of the potassium atom, right? So it loses an electron, and removal of an electron from potassium is an endothermic process, so it's a positive energy change. At the same time, there's also the attachment of the electron on the bromine molecule, and so there's a negative exothermic, negative EA, right? Negative EA here, negative electron affinity is supposed to have a negative value, but here they put it as a positive value, so when you minus it away, it becomes a negative value, right? Then there's also finally the last energy change, which is the decrease in the electric potential energy. So this may be more H2 physics students who have learned the topic of electric fields would be more familiar with this expression, right? 1 over 4 pi epsilon naught times Q1 Q2 over R. That is the change in the electric potential energy, right? And E here doesn't refer to Euler's number, it refers to the elementary charge, which is the charge of an electron, 1.60 times 10 to the power of negative 19 coulombs. Right, so these are all constants. Yeah, and R is the distance between the two particles, between the potassium and the bromine. And so, with this expression for the overall energy change delta E, how do we calculate what is this maximum distance, right, between the potassium and the bromine molecule in order for there to be electron transfer to occur? Well, we have to think about when is this energy change energetically feasible? When is this process, this electron transfer, energetically feasible? It is energetically feasible when delta E becomes negative. In other words, when the process becomes exothermic, right? When the process gives off energy. And so, at which point, if you plot a graph of delta E against R, when will there be a turning point, right? Not turning point. When will the delta E cross the x-axis? When will delta E become negative? So at the point where delta E is 0, right, when it crosses the x-axis, right, that is when the process will start to become more and more energetically feasible, right? And so we simply just need to sub in delta E equals to 0, right? Delta E equals to 0, and sub in the values that we take from database of the ionization energy, of the electron affinity, and of all the constants, and then we solve this equation for R. That value of R would be the maximum distance between potassium and the bromine molecule, for there to be a electron transfer to occur between the K and the Br so that the reaction can proceed. So that would be the maximum distance. Yeah, so if you want to be more mathematically correct, you can solve an inequality and to get R to be less than or equals to a particular value. That is the maximum distance, right? At which point the electron can jump, right? Okay, so that was a bit long. So I hope that you could understand the explanation, right? It wasn't too convoluted. If you can't understand the mathematical part, it's alright, as long as you can understand, how the harpoon mechanism works. I mean, I think it's quite, with the analogy of the fisherman, the harpoon, and the fish, I think it sort of makes sense, right? I mean, it would be best if I could illustrate this with some sort of animation or a video, but unfortunately, I don't have the technical expertise to produce that. So for now, I can just only show you this illustration here on this piece of lecture note. So I thank you for viewing this video. I've come to the end of this presentation, right? End of part 1 of my kinetics presentation. I still have part 2, right? All part 2 stuff. So I may be going through part 2 another day, maybe tomorrow, maybe another day when I'm free. I hope you did learn some stuff on kinetics, right? And if you're really interested, do go read up this book. It has 2 or 3 chapters on kinetics, and as well as not just all these conceptual stuff, but also higher level mathematical treatments and techniques in the book, which for those who are more mathematically able, you may can go and take a look at those stuff. Yeah, so for those who are interested in what the second part of the presentation would be, maybe you can go and consider these questions, right? So I'll be covering special cases for the activation energy. When is it equal to 0, and when will it be negative, right? So we can go and take some time to ponder on these questions before I review the explanations and the answers in the next part of the presentation. Alright, with that, I think I will end this presentation. Before that, one more thing, I would just really hope that you can internalize the steric and energetic requirements for an effective collision, right? So represented by this more complete version of the Arrhenius equation. So typically we don't consider P, because P is really sometimes not very significant, right, in our calculation. I mean, it doesn't really enhance the calculation too much, because I mean, for most of, I mean, the more advanced treatments, right, in kinetics, also doesn't really require this P value. I mean, sometimes perhaps the A takes into account the P. It's not that they are P and A become a single constant. So sometimes that's the case, yeah, in a lot of the work that we do. So yeah, but anyway, just I hope they can appreciate that you need to take into account both the steric and the energetic requirement. And I think that is the point that I want to drive home, right? In this presentation. So with that, I think I will really just end this presentation here. Thank you for viewing this. Hope you learned something.